Welcome back, class. I'm Dr. April Ström, and in this particular video, I'm going to showcase yet another example of the power rule. It turns out, though, in this function that we have s of x equals 5x cubed minus 6x squared plus 4x minus 8, we had several, in fact, 4 miniature power functions kind of laced together with positives and negatives, with plus and minuses. So we're going to find the derivative of this whole function, which will require us to find the derivative of each of those 4 terms. And each of them essentially requires this power rule here. So just as a reminder, if we have a function that's a power function, say x to the n, and I wanted to take its derivative, I just need to bring that power down in front, multiply by the x that's there, and then subtract 1 from the old power. So let's do that here. I have s prime of x is equal to, again, I'm just going to go term by term. So I check out here 5x cubed. Using the power rule, I'll bring that 3 down in front, but just don't forget that because I already had a 5 hanging out here, I need to multiply those together, the 3 times the 5. So when the 3 comes down in front, I end up with 15x, and then I will subtract 1 from that original power. So 3 minus 1 is 2. So the derivative of 5x cubed is 15x squared. Then I will subtract the second term's derivative. I have 6x squared, so once again, I will take the 2, bring it down in front, multiply by the existing 6. So I have a 12, and I have now x being multiplied by the 12, of course, and the new power now is 2 minus 1, which is 1, and I could write it right here or not. I'm going to write it just so you know exactly what number is there, but you don't have to. And the third term here, 4x, I've got to take its derivative, so I'm going to add here the derivative to 4x is simply just the coefficient in front of that term. If you'll recall, we're taking these powers, and right now, that's a power of 1, and we're supposed to take that power in front, multiply by the existing coefficient, subtract 1 from that old power. So if I do that, when I bring down the 1 in front of the 4, 1 times 4 is, of course, 4. But then I end up with x to the 0 power, x to the 0. Because I have 1, subtract 1, I'm now at 0, x to the 0. Well, it turns out that anything but 0 to the 0 power is just 1. So we don't have a way to indicate what 0 to the 0 is, okay? But we do say anything that's not 0, but taken to the 0 power will just be 1. So as a result, we don't need to write this x to the 0. Literally, it's just going to be the number 4. That's where 4 times 1, just 4. And then we carry on over here. We've previously learned that when we take the derivative of just a constant, you notice the 8 has no x near it. So this is just a constant number. When we take its derivative, it's just 0. No need to write it. So this is it for the derivative of s of x, which is 15x squared minus 12x to the first, or just 12x, plus 4. Now, let's say I wanted to find the second derivative of s. So s double prime of x. And this just means the second derivative, or it means the derivative of the first derivative. So I can repeat that whole process of all these power rules and find now the derivative of this answer that I just got. So let's do that. That'll be our second derivative. So I have my first term here. Once again, take the power of 2 down in front of the 15, multiply those together. We have now 30x, and I need to subtract 1 from the power. So 2 minus 1 is 1. So I have x to the first. Again, you can write it or not. And then we will subtract off over here. This is very similar to like that 4x term I had. I have just a coefficient times x to the first power. If I can think about the power rule again, I bring the 1 down in front, multiply by the 12, I get 12 again. But once again, I subtract 1 from the power, that leaves me with 0. X to the 0 is just 1, so therefore we just have minus 12. And then lastly, like with the -8, I have a +4 here because it's a constant number. When I take its derivative, that term's derivative is just 0. So now I have a second derivative that literally is 30x minus 12. One more time, check this out. What if I wanted to take the third derivative? So s triple prime of x. So in the same way that the second derivative was the derivative of the first derivative, and the first derivative is the derivative of the original function, the third derivative is simply the derivative of the second derivative. So here we go, more power rule stuff. I have 30x minus 12, I take its derivative, I had a power of 1 here, bring it down in front, multiply by the 30, I still get 30. But then I have to subtract 1 from the power, which gives me a 0 power. Once again, x to the 0, just 1, 30 is it. But then I have the minus 12, just like before, just a constant term. When I take its derivative, it's 0. No need to write it. I end up with just 30 here. And if you're a super rebel, let's do one more. What if we wanted to do, say, the fourth derivative? Notice how I wrote this. Before I said s prime for the first derivative, s double prime for the second derivative, s triple prime for the third derivative, but yet here I changed to a number. We do that after the third derivative, we switch to numbers because there's just too many primes to have to write them all. So this means the fourth derivative, or in essence, the derivative of the third derivative. Well, the third derivative was just a constant number 30. So as you might imagine, the fourth derivative, which is the derivative of this function, since it's just 30, constant, the derivative is just 0. So now I have a function that by the fourth derivative, I get 0. Now you might be asking, does this happen every single time with every single function in the world? No. It will be the case if you might notice, going way back up here at s of x, that was just a polynomial function. A polynomial is a function that has several terms and 2 integer powers, in fact, positive integer powers. And at some point in time, depending on where we start in our original function, at some point in time, if I do enough derivatives of that polynomial function, I will get one of the derivatives eventually to be 0. But not every function in the world works like that. But here are some examples of how we can keep finding the derivative of a derivative of a derivative and so forth. We will learn far more about the second derivative, its interpretation, its graphs, all kinds of fun things as well. So that will be coming soon. So I hope you enjoyed this video. Please be sure that you like the video and subscribe to our channel for future videos. Thanks.